So good morning, good afternoon, good evening, depending where you are. First of all, I would like to thank the organizers of SNAQs for this kind invitation. It's a real honor to be the first speaker in this series. Actually, well, I'm impressed by the number of registered participants, so nearly 300, about 200 already online. And at this stage, I feel forced to ask you to lower your expectations somehow, okay? At least for the first talk. I'm sure that you will be able to raise your expectations back for the second and third talks today. But the first one is going to be a very, very simple overview on stellar evolution, a primer on the evolution of stars with emphasis on nucleosynthesis, that is on the cosmic origin of the elements, and on the astrophysical sides where these elements are actually being created. As I said, this is an overview, and in 45 minutes, obviously I cannot really enter into details, but I hope to raise questions and aspects that will be covered in detail in future SNAQs. Okay, this is aimed for students, and particularly for students that do not have a strong background in astrophysics. All right. Yeah, actually, the theory of stellar evolution relies heavily on astrophysical modeling. Okay, those models, however, represent some sort of a crucible where different branches of physics merge and complement each other, and this includes theoretical and computational astrophysics. I hope you can see the cursor on the screen. Observational astronomy, either ground-based or spaceborne. Also, a theoretical and experimental nuclear and atomic physics, and last but not least, cosmochemistry. I'm convinced that all of you feel close to at least one of these different boxes on the screen. I would like to start this talk with some past memories from a long time ago, that's it, but not from actually a galaxy far, far away, since the story that I'm going to tell you happened actually really, really nearby. When I was 7 years of age, I was in a bad physical condition. I spent almost a year at home in bed with high fever. Okay, I almost missed an academic year. My mom actually was in charge of my academic progress, and she was supervising my homework. And just to improve my mood, she was bringing home from time to time some comic books. One of my favorite characters at that time was Flash Gordon. Okay, that may sound familiar to some of you at least. Okay, and in one of the stories of Flash Gordon, which I picked out for this talk, written in 1958, I wasn't born yet. Actually, Flash and his girlfriend Dale Arden were captured by an evil race of aliens. There's always some evil race somewhere. Okay, so when they were exploring the dark side of the moon, these two humans were captured by this evil race with the purpose for the aliens to actually investigate how smart humans were. Actually, they wanted to determine the IQ of humans. Okay, to that end, they perform a number of experiments on Flash and Dale, and in particular, in one of those experiments, they enclosed them in a room, and progressively they started to remove the air from it. Okay, obviously, humans began to suffocate. Okay. But before fading away, actually Flash, who was a smart guy, saw something unusual in one of the walls, actually here. He saw a strange collection of boxes written in a, hard to understand language. It was an alien language after all. And the idea is that, well, at some point, the layout sounded familiar to him. And just before the last moment, he actually got some sort of a flash in his mind. And he said, wow, I know what it is, okay? And you can read here in the text, this is apparently, according to him, the alien version of the the periodic table of the elements, actually. And because Flash was a smart guy, and he remembered from childhood the location of all the elements in the table, he pressed two boxes corresponding to, according to him, the location of nitrogen and oxygen, and after that, a breath of, some fresh air filled the room, and they were all safe. Well, that happened to Flash. Wow, you can imagine, I was reading that when I was 7, okay? So imagine my surprise. I was really excited. I remember jumping out from bed, and taking my diary actually, and in the chapter of important things to learn in life, I wrote down in capital letters, learn about the periodic table. One day it can save your life, okay? Well, I must confess that to date, the periodic table didn't save my life, but at least it pays my salary, which is not a bad thing. Now, that said, I wanted to ask you, all of you, how many would be capable of recognizing the periodic table out of this layout? Honestly, not me, because I'm more familiar with the different arrangement of the elements on a table. Something like this, with you know, hydrogen on the upper left corner, not down, not up there. Yeah, the noble gases on the far right column, and then the rare earth elements, for instance, somewhere aside at the bottom, you know, separated from the rest of the elements. Actually, the layout that the writer used for this strip of Adventures of Flash Gordon was based on the original layout that Mendeleev, you know, proposed basically 150 years ago. Okay, this is a picture of a monument devoted to Mendeleev and his periodic table that you can see if you walk around in the streets of St. Petersburg. That's funny because, as I said, the original comic book, the original strip I picked it up was from 1958, and already in 1905, people like Werner, scientists, actually ended up rearranging the location of the elements in a more suitable form that is pretty close to the one that we probably all of you have learned in school. Okay, so it's hard to say, well, I mean, Flash had incredible memory. He didn't not only know the location of the elements in this, you know, arrangement, but also in the previous ones from Mendeleev. That saved his life. Well, as an adult, I must confess that I switched my interest on the periodic table to understand what is the origin of the different elements, where the different elements, the more than 100 elements, have been created. And I have always found fascination on a number of plots related with the origin of the elements. For instance, this one. Here on the left, you have a plot in terms of elemental composition. So I'm not talking yet about isotopes, just about elements. Okay? So this is a picture somehow describing the composition of the early universe in mass fractions. Okay? So remember that when mass fractions are some sort of proportions of the elements that when added together for a given sample, the different mass fractions of all the different components, at the end, the summation is equal to 1. Okay, and this is in log scale down to a threshold value that I picked up 10 to the minus 12 in this particular case. Okay, so you can see that the early universe, as most of you, I'm sure, know, was chemically very poor, consisting mostly of hydrogen and helium and just traces of an additional element that was lithium, actually. But today's picture, today's pattern, chemical pattern, is totally different. This is, for instance, the composition of a human, the elemental composition of a human being with using the same threshold value here. It includes about 60 different species. Okay. Well, how we switch it from that composition in the early universe to, for instance, the composition of a human being is the result, is the relic of a number of nuclear processes, something that we call nucleosynthesis. Okay, that has been active for millions of years in the universe. And actually that would be one of the main motivations of this talk, okay? To actually understand where the different dots are actually coming from. And we will see that this is mostly the result of nuclear processes occurring within stars. I say mostly because, as I mentioned previously, some of these elements have been also synthesized during the Big Bang. And then there are additional processes like cosmic ray spallation, for instance, that is the main mechanism for the synthesis of a certain group of light species, like isotopes in the lithium beryllium boron group. And also they contribute to some extent to the abundances of intermediate mass elements. There are different ways of showing similar arrangements, in this particular case for the solar system. I'm sure we'll see that plot in the next two talks by Chris and Aurora today, so I can skip the detail. Just let me emphasize that this specific pattern here that is characterized by some sort of an exponential decay in the abundance of exponential curve, describing the abundances of the elements when increasing the atomic mass, and superimposed to that a number of peaks is the result of nuclear physics effects. The fact that there is a peak, for instance, around iron is just the result of the largest binding energy per nucleon of iron-56 with respect to the neighbors. And this basically reflects that nature favors certain configurations in terms of magic numbers, certain configurations of nucleons. So arrangements of neutrons and protons in the nucleus, in the corresponding nucleus, okay? And basically the magic numbers reflect a closed shell configurations within those nuclei. Okay, probably we'll hear more about that from Aurora. In essence, what these different plots are showing you is that we are the result of a star stuff. Okay, we are the product of nuclear processes occurring in the stars. And in the case of our bodies, the carbon in our flesh or the nitrogen in our DNA have been generated in stars, but also around us. For instance, the oxygen that we breathe, or the calcium and iron in the cereals that we eat for breakfast have been synthesized within the stars. Okay, this is an example of some cereals that I don't know whether you can read the screen. Actually, they say they provide you with a good source of calcium and an excellent source of iron. Unfortunately, the chemical system that the chemical symbol that they use it here to depict iron, it's not probably the one that you will pick up as an expert and as experts in nuclear astrophysics, right? So the question that maybe you may be concerned at this stage. So what the hell are we taking for breakfast? Okay, are we eating iron-rich or iridium-rich cereals? Iridium is not the thing I would recommend you for breakfast. I mean, it's not the healthiest element in the periodic table. Okay, but again, I think that you all can calm down, because if you think about the price of a box of cereals and you compare the prices of, for instance, iron and iridium, you will realize, well, these cereals cannot be really a lot of iridium rich. Okay, otherwise the price will escalate for cereals too. Now, back to the primordial nucleosynthesis. Just let me remind you something relevant. I wrote down throughout my talk a number of takeaway boxes with some important messages for you, for the students to take back home. Okay, so remember that the Big Bang nucleosynthesis, so the first nuclear processes that occur in the early universe, ended up generating basically a universe that was mostly dominated by the presence of hydrogen and helium-4, with just traces of two of their isotopes, so the deuterium and the light helium-3, lithium-7 too, right, at the level of 10 to the minus 7%. Okay, remember that the Big Bang nucleosynthesis is a very interesting story about, achieving the right conditions, thermal and density conditions for nuclear reactions to occur. Okay, early on, the universe was too hot to allow the assemblance of complex species based on combinations of protons and nucleons, and later on, because of the expansion of the universe was too cold for nuclear fusion to proceed. So primordial nucleosynthesis took place on a time scale of just a few minutes. So essentially, 15 minutes, in the first 15 minutes of life of our universe. That composition mostly remained frozen. I say mostly because, well, you could expect some spallation reactions and similar effects at that epoch, okay, that may have induced some changes to some extent. But it was not until several million years later, when the first stars formed, where changes in the chemical abundance pattern of the universe started to appear in a significant way. Well, once the Big Bang was discarded, people turned the eyes to the as the sites for the synthesis of the element to stars. And based on previous work, probably the most complete theory on stellar on the creation of the elements in the star was initiated with the work by Fred Hoyle in the mid-1940s. But of course, all this work and follow-up papers required some sort of observational smoking gun evidence of the role played by stars in the synthesis of the elements. And this was achieved by Merrill, who detected the presence of technetium in the spectra of a certain type of stars. So what is relevant about technetium? Well, all the way, again, back to the periodic table, all the way from hydrogen to lead, okay, all the elements in the periodic table have at least one stable isotope, except two, okay? So probably Flash knows how, which ones do not have a stable isotope because he knew the periodic table by heart, right? So these two elements are promethium, an element in the rare earth region, and technetium, a metal, okay? In particular, all technetium elements are radioactive, and the isotopes that have the largest half-lives among the set of isotopes of technetium, if I remember correctly, they are technetium 97 and 98, both have a similar half-life of about 4 million years. Well, if we live in a universe that is about 13.7.8 giga-years old, and we are observing yet technetium, which has a half-life of just 4 million years, that means that this element cannot be primordial, could not be generated. I mean, all the technetium that we see today could not be made at the moment of the Big Bang. It has to be a more recent history, okay? And that was the first evidence that stellar nucleosynthesis, because that element was detected in the atmosphere of a star, was an ongoing process, okay? That was something achieved in 1952, and since then we have observed additional, radioactive species, even more short-lived, okay, that demonstrate that nucleosynthesis is an active process still going on. Well, probably you're familiar with the way stars form. They form in these beautiful clouds, regions of, hydrogen-rich that pollute the cosmos in the so-called stellar nurseries, places like this, beautiful. And for those that are not pretty much familiar, the driving force for the formation of the stars is gravity. Okay, when you have all the time of the universe available to build up structures, gravity, which is a slow and not the strongest force in the universe, the weakest, is capable of reassembling big amounts of material. Okay, so when you are actually doing that within a cloud, essentially you are forming protostars by arranging a certain amount of mass. And at some point, this contraction, this progressive contraction stage, stabilizes when matter starts to exert a certain amount of pressure. At the end, you reach some sort of stable structure, a equilibrium, in which gravity is compensated by a pressure gradient. At the temperature and density conditions that operate at the stars at the moment they are born, the pressure, the equation of the state describing the plasma is a function of the temperature. And recall, in the case of a star, actually that's the definition of what a star is power by nuclear reactions operated at the center. I will come to that point later. Okay? These nuclear reactions are a source of energy. They release energy and they maintain a certain temperature, so a certain pressure, and then that is what balances gravity. Any change in the temperature of the star can induce, an overpressure with respect to gravity, so the whole thing will expand, or a lower pressure. In that case, gravity dominates and the whole structure contracts. Okay, that brings up something to your mind, which is, okay, yeah, I understand gravity and pressure at some point are balanced, but depending on at which central temperature this balance is established, you may or may not ignite a nuclear reaction. Think about a planet like Earth, for instance. Okay, essentially the mechanism of formation is similar to a star. Okay, but in essence, what we get is a structure that has been stabilized with a central temperature of a few thousand degrees, which is pretty hot for a human. Okay, but again, not enough to power nuclear reactions. And this is the main distinction between planets and stars. Essentially, both are structures stabilized between gravity and, in which these are, structures where we have a balance between gravity and a pressure gradient. But depending on the temperature at which this equilibrium is achieved at the center of the object, we have nuclear reaction and then stars, or we have no nuclear reactions at all, and then we have planets. Okay, I will come to the point later on this minimum mass required for that. Now, our sun, okay, seen here in X-rays, in a more menacing image than the usual view of the sun that we can have with our naked eyes, releases a power of 10 to the 26 watts, so 10 to the 26 joules per second. I mentioned that this is due to the existence of an internal energy source, nuclear reaction, okay? And probably you learned from kindergarten already that when dealing with hydrogen burning, there are two main mechanisms for establishing nuclear fusion. So either the proton-proton change or the CNO cycle. In some more massive stars than the Sun, the CNO cycle actually plays a leading role. But for the case of our Sun, this is mostly due to the, to the PP1 chains. Okay, so proton-proton chains as depicted here on the slide. Okay, in essence, what you have is 4 nuclei of hydrogen that are assembled into a nucleus, an alpha particle, a nucleus of helium-4. Okay, releasing in the process about 26.7 mega electron volts. So you have the number here in joules. Okay, well, I put the number in joules basically because remember, I mean, per second, that's the amount that the Sun releases, 10 to the 26. So this is telling us that, a lot, but a lot with quite huge capital letters, a lot of nuclear reactions are actually taking place per second within the Sun to actually power, such amount of energy. Since this is a school, I prepared a set of exercises for you guys, okay? And one of those that you can do at home at your leisure time is to find out that our Sun burns about 600 million tons of hydrogen per second to explain such amount of, to explain the power output from the Sun, okay? Well, these numbers sounds like a lot, but I mean, the Sun is pretty big, okay? And so the amount of hydrogen available in the Sun is incredibly larger than that. And that raises two questions, okay? The first thing is that, well, we can, another view of what a star is like a nuclear power plant, so powered by nuclear reactions. So it requires some fuel to maintain, to be turned on, okay? So at some point, the Sun will consume all the, fuel at the center, and it will turn off. And obviously, this may have consequences for us, okay? So that's an important thing that probably all of you know. But there is a second interesting question, okay? 600 million tons are just of hydrogen are just peanuts compared with the total amount of hydrogen that the Sun has, okay? You can calculate that. And then the question is, why not all the hydrogen in the Sun undergoes nuclear fusion simultaneously? Okay, well, think about it. What we are dealing with is, imagine that you have a tank full of gasoline, okay? And then you approach a flame to that. Then what we are having in the Sun is like only a small region of this gasoline in the big tank is actually being burned, okay? But probably it's not what you expect. I mean, you would expect the whole tank to blow away, right? So why is it? Well, Aurora will tell us why, probably, okay? This is the result of quantum tunneling, the low probability of nuclear reactions to occur within stars, among other factors, okay? So we'll hear along this session more about why, and we are very happy about it, why not all the nuclear fuel in the Sun is consumed in a blink of an eye, so to speak, blowing up the whole structure. Okay, something else. Yeah, we have learned that through the proton-proton chains, we can liberate energy. But also, as you can see here, for instance, stars also produce gamma ray photons. And this is also interesting because gamma rays do not go very well with life. So the question is, why are we here, okay, if we have a source that generates so many gamma rays relatively nearby, okay? You know the answer, right? The answer is all these gamma rays do not appear at the surface of the Sun, at the photosphere, as gamma rays. They lose energy in between, traveling through the 700,000 kilometers of radius of the Sun. Okay, some sort of a random walk, interacting with the plasma in there and losing energy, which makes them to emerge as not so harmful visible photons, right? The physical concept here to illustrate that is called the mean free path. This is the distance traveled by a particle, a photon in particular, without interacting with the environment, okay? In the case of the Sun, for a photon, the mean free path in average is about 1 centimeter. If you take average values, it could be much shorter than that. That's the distance traveled without any, interaction or losing energy by a collision with the other particles in there. Okay, close to the center is smaller than that. So take these numbers to evaluate second exercise today, these images. Okay, I hope you know this guy. This is Captain Picard from one of the spin-offs of Star Trek. And in one of the movies made out of this series, in Star Trek Generations, we are facing an interesting situation. There is an evil scientist, you see, again, an evil guy, that actually has invented a device that can actually inhibit nuclear reactions in stars. And actually, to demonstrate that, he sends the device to a star similar to our sun. This is not our sun, hopefully, okay? And you can see that, yeah, immediately the sun, the object, the star, turns off. The question I ask you is about the feasibility of this sequence here. Well, you can imagine there is a device that inhibits nuclear reactions in the center. But what happens with the photons that have been traveling throughout the plasma and will take forever to emerge at the surface? Remember, I mentioned the mean free path in the sun is about 1 centimeter. So if you assume the same thing here, you will get at that the typical time scale for the photons to be emerged through the photosphere of the star, of the sun, would range, depending on how you do the calculation, whether you take mean values or do the exact thing, say between 10 to the 4, 10 to the 6 years. Okay, so the thing would be correct, provided that Picard takes between 10 to the 4 and 10 to the 5 years to look at the star and then look back. Okay, well, then you can see whether that's feasible or not. More details. More details about the sun. Yeah, we know that the sun has been working as an engine on the basis of this nuclear fusion of hydrogen for a while. Actually, stellar evolution models, standard solar model in particular, which I hope will be the topic of one SNAQs in the future, tell us that from the original about 70% by mass of hydrogen present at the core, this has been reduced by almost a factor of 2, right? To about 34%, in turn increasing the amount of helium close to the center. These compositional changes have translated into a number of structural and changes within the sun, in particular, and dynamic changes. Okay, the surface luminosity, so the brightness of the star, has increased by 40%, and the radius has changed by about 10% or so. Okay, how these numbers have affected the life conditions in our planet in the past 5 giga-years are a matter of debate. Okay, but certainly one can expect at least some effects up to some level. So what will come next? Because yeah, these numbers are decreasing. At some point, we will get rid of hydrogen, and so at some point, the sun will turn off. Okay. Well, this is illustrated by this sequence here. At some point, the hydrogen at the center will be gone. Don't worry, no rush for that. I mean, we have to wait until 4 or 5 giga-years from now. And because of these structural changes, the sun will increase its size to what is called a red giant configuration. Okay. In order to understand the evolutionary changes that the star can undergo, astronomers have invented what is called the HR diagram, or Hertzsprung-Russell diagram, in which you place the stars when they are actually beginning to operate as such, so burning hydrogen at the center, in a band, okay, when plotting the luminosity or brightness in the vertical axis, and then the effective temperature, which increases right to left in those diagrams. Here you can, I mean, this is something that you can obtain by very simple quantum physics laws, so Wien's law, provided that you know the luminosity and the radius of the object, for instance, okay? Well, you can see diagrams like these with the effective temperature or with the masses of the stars. So low mass objects here, you know, the highest mass, more massive stars on the left-hand side. The sun is here. So interestingly, all the stars, when they start to burn hydrogen, so a scheme like this, so burning hydrogen at the center, and then the rest is, you know, essentially an inert plasma there, yeah, occupy a location, a particular point in this diagram. If the star is like the sun, somewhere there, less massive than the sun on the right-hand side, more massive than the sun on the left-hand side, okay? And here I could spend the whole afternoon with this slide because, as you can see, it's a little bit more complicated, but let me go quickly. At some point, the star will run out of fuel, so all this hydrogen will be converted in inert helium there, yeah? And then what happens is, because you run out of fuel, gravity wins and the star begins to contract, okay? And you can imagine that the hydrogen that was not burning, but it was very close to this central region of hydrogen burning, will achieve, because of contraction, it will heat up, yeah, and will achieve the critical conditions to undergo nuclear fusion. So the next stage will be dominated by hydrogen burning or hydrogen fusion in a shell, surrounding this inert helium core. Okay, this is called the red giant star. This has this induces structural changes, and the idea of the star reaching giant dimensions. Okay, so then what happens? Well, that's the funny part about nuclear physics. Okay, if in the contraction of the inner core you achieve high enough temperature, and who will determine that? Well, the amount of mass that the star has. The more massive the star has, the more intense or more important the gravitational pull will be. Okay, and so more massive stars will achieve larger central temperatures easier, so to speak. Okay, at some point we can reignite these helium-rich ashes from hydrogen burning, and you will have a core helium burning star, okay, surrounded by a layer of inner helium, surrounded in turn by a layer of hydrogen burning, and then the inert outer envelope. Yeah. Well, and at some point, this helium at the center will be gone, exhausted. We will end up having something that is carbon-oxygen rich, and then two shells surrounding that, one in which you have residual helium burning, the other one in which you have hydrogen burning, and the outer envelope of the star. This configuration is of particular interest. This is called an Agb star, a syntonic giant branch star, somewhere there, okay? And these are the sites for the S process, the synthesis of elements, about half of the elements more massive than iron in the periodic table, okay? So that's the destiny that awaits to our sun. Our sun has enough mass to undergo hydrogen burning, central hydrogen burning, central helium burning afterwards, reigniting the ashes, okay? And it will become an object that is mainly made out of carbon and oxygen at the center. The outer layers of the sun will be expelled in what is called a planetary nebula, an object that is very beautiful. You have here some examples of them, okay? Beautiful images. Complicated as hell, and as you can see, there are different geometries that depend not only on the viewing angle, but on the number of parameters like, the spin of the stars, the composition, the mass of the different objects, whether they have binary systems involved or not, a number of things. So still a lot of work to be done to understand the geometry of planetary nebulae. Good. Exercise number 3. Well, I don't know whether you have seen that movie. It's one of my favorites from the 50s, When Worlds Collide, science fiction movie. It's one of those movies from the subgenre of catastrophic movies, or, an object in a collision course, like Armageddon. Okay? But in this case, it's not an asteroid. It's actually a real planetary system going in a collision course towards the Earth. In this case, probably the budget of the movie was not that, big. And they had it's a planetary system with just one planet, okay? And but the star is a nice star, is a red giant star. You can see it's red, okay? Yeah, it's red because we see it. But how giant is that star in the movie? In the movie, they tell us this has 12 times the size of the Earth. Okay, so in terms of units of the solar radius, that's about 10% of the solar radius. Okay, well, let me tell you that the biggest red giant stars, which have a size of about 1,000 or even 2,000 solar radii. So, I mean, that's what we call them giant, okay? An object like Velos, actually, you can use some, scaling factor laws and so on to estimate. It will have the mass of Jupiter, more or less, okay? And that's much below the minimum mass to actually ignite nuclear reactions in the star. So below the threshold mass that defines a star. Actually, that value is about 8% of the mass of the sun. That's the minimum mass that actually is required to achieve enough temperature when when the pressure gradient compensates gravity, okay, to ignite, to achieve high enough temperature at the center to ignite nuclear reactions. Jupiter would require about 80 times its mass to achieve that value. Okay, so well, I mean, catastrophic. I mean, if Jupiter will collide with us, that would be the end. Okay, so you don't need to go that big. Okay, but if you call a star giant, make sure it has the real size. Okay, good. Okay, this can go on and on and on. I only have 15 minutes to go. So let me accelerate here a little bit. And let me make a division saying that everything below 10 times the mass of the sun has a similar fate. Okay, actually up to, say, 8 solar masses, more or less, okay, all stars will have a similar destiny than our sun. They will undergo only 2 fusion stages, hydrogen burning first, like for any star, followed by the reignition of the ashes through helium fusion, okay? And then they will end up being those objects that we call carbon-oxygen white dwarfs that I will redefine a little bit more in a moment, okay? In the range between 8 and 10, you know, stars can undergo the reignition of these carbon and oxygen-rich ashes, okay? Actually, they can undergo carbon fusion, okay? But when you exceed about 10 solar masses, and these limits are really not very well fixed and determined, depend on a number of parameters, stars may undergo the full sequence of nuclear fusion. So first hydrogen, then helium, carbon, neon, oxygen, and silicon, and that's it. Don't think that, you know, stars can undergo like 20, 50, 60 different stages of nuclear fusion. They are a handful. Okay, the last one is silicon burning, okay, which for the case of a massive star can last for essentially 1 day. Okay, why silicon is the last product, the last element to be fused in stars? This is related again to the binding energy per nucleon. Remember I mentioned, I mean, iron is among the, iron 56 is among the elements. So you have here the 3 guys that have the largest values of binding energy per nucleon, okay? The idea is that by fusing lighter species up to iron, you can release energy. And this release of energy helps to establish a given temperature and a given pressure, and so compensate gravity. But once you reach iron, any atom to undergo nuclear fusion with heavier species will not involve an exothermic process. It will consume energy, so it will not help to stabilize the star. So that's why silicon burning, transforming the center of the star into an iron group elements, is the last stage of evolution of a normal star. Let me just mention that you can produce things release energy based on heavier species through fission of heavier elements down to more lighter species. Down to iron in this case. Okay. Good. I will just skip that slide. I will skip it, but I keep it on my on the PDF that will be available to everybody to give you a flavor on the numbers of the masses required for the different fusion stages. So 0.08 to actually burn hydrogen. So that's the division between planets and stars. Around 0.25 solar masses to burn helium, 8 solar masses to burn carbon, and about 10 to burn everything. So to summarize what happens with the stars, this is what I would like to say. I mean, stars below 10 solar masses have a similar fate than what will happen to our sun, okay, to our star. Okay, they will at some point become red giants. In the process, by the way, the Earth will have a very bad day. Okay, so it would be either engulfed within the size of the red giant configuration that our sun will attain, or other models suggest that maybe it will not be completely embedded within the red giant, but the surface temperature in our planet will be several thousand degrees, so we will incinerate everything. So not a good place to be that day. Okay. In the process, remember, the outer layers, maybe several tens of solar mass, will be ejected in the form of planetary nebula. For those not living in the solar system, it would be a beautiful image to see. Okay. For those still in the Earth, well, not the best way to to watch it, okay? And what will remain of the original star is written here. It's called a white dwarf, okay? White because of a color code associated with a position in the HR diagram, and dwarf because from the original sun, the remnant will be an object that will have the size of a planet, okay? So much smaller, like between 2 and 3 orders of magnitude smaller than our sun, okay? Something like that. And the maximum mass that the white dwarf can have is 1.4 solar masses, not a problem for our sun. But yeah, that means that imagine a star of 8 solar masses will need to, lose, something like 6.6 solar masses, okay? The residual will be 1.4 solar masses. The rest will be lost in the form of a planetary nebula or so, okay? Now,
5 minutes warning.
Okay, fine. So more massive stars will have a more dramatic fate. As I mentioned, they will undergo the different nuclear stages, nuclear fusion stages, and they, instead of ending their lives in a gentle ejection of the outer layers, in a non-explosive way, like in the case of a planetary nebula, they will experience a real explosion, like a type 2 supernova, for instance, as depicted here. From the original star, the remnant will be only either a neutron star, if the mass containing that remnant is limited to, say, between 2 and 3 solar masses, the size of a city, 10 kilometers, okay? Or then a black hole if, the mass is larger than that. Well, the question is that, fine, yeah, I hope that you catch the whole picture. That's the big picture of a stellar evolution of the stars. But I mentioned here type 2. Okay, and even the jargon in astrophysics is not very clever. I mean, we are not that crazy to start naming things by number 2. Okay, so somewhere hidden, maybe, we should have type 1 supernovae, but they do not appear here. Well, the reason is that most of the stars in our galaxy, in particular, 50% of the stars are not isolated. They form double or multiple systems, some of them even interacting, okay, and some of them even showing that at some point in their evolution, one of the stars get engulfed within the giant dimensions of the secondary. They undergo a period of the evolution which is poorly known, that is now a common envelope phase. Okay, so as you can see, the secondary is engulfed within the outer layers of the primary star. Out of this, we know that some of these double or multiple systems observed in the galaxy, some of them form what is called a compact binary with, for instance, a white dwarf or a neutron star in there. Okay, and in some of these systems, the orbital period is that short that we allow, the secondary is actually entering in the area gravitationally dominated by the strong gravitational field of the compact object, and so mass transfer episodes ensue. Okay. So in my last 1-2 minutes, I just would like to say that this is the way in which we can revitalize stellar corpses. So an isolated white dwarf or a neutron star will just cool down, nothing else will happen, but we can revitalize them, transforming them in some sort of zombie stars, I mean, coming back from death, okay? And actually in the mass transfer from a companion onto a white dwarf or neutron star, we can have a blend of explosive phenomena. This is where type 1 supernova occurs. Also, we can have nova explosion and X-ray bursts. Okay, so just to finish, let me say that attendees will find in the next slides some slides just describing, the properties of those objects. So my talk is gone. I have exhausted the time as expected. Okay, let me just say that sometimes you can have 2 compact objects that merge and collide, like in the case of white dwarfs here, or in the case of neutron stars. These are simulations, for instance, performed in our group at UPC in Barcelona of a head-on collision of 2 neutron stars. This is precisely the topic of the next SNAQs, so the origin of the relation between our process elements and neutron star mergers, so you can skip that completely. And as I said, just for your information, in the next slides, in case you are interested, you will find some summary, some greatest hits of which are the main properties of novae, okay, which is the nucleosynthesis endpoint, their nuclear uncertainties, the same for type 1 X-ray bursts, okay, and the same for I can move, yeah, and the same for supernova. Okay, this was a very, really wide topic. I didn't have time to cover it with a minimum detail, all the aspects, but I'm not worried because this is just, like the preamble for a number of talks in the SNAQ session. So I would like to stop here, and I would like to thank you for your attention.
Thanks, Jordi, for the very nice talk. There are quite a few questions. I'll start with this one. How much material is ejected into the interstellar medium when a planetary nebula appears? How does this compare to the material ejected, by example, by type 1a supernova?
Okay, good. So let me put it that way. Well, it's hard to define because planetary nebula are not long-lasting objects. Okay, so the estimates, it's not the area in which I particularly work, but from what I know, a planetary nebula can last for about 10,000 years typically. Okay, so that means that at the end, all this material that is in the form ejected from the original star, that is in the form of a planetary nebula, will contribute to interstellar material. It's just a matter of 10 to the 4 years. Okay, so I mean, usually the answer to that question is we know what remains as a white dwarf, depending on the original, on the mass of the original star, up to 1.4 solar masses, and the rest will essentially be part of this interstellar medium sooner or later. Compared with the type 1a supernovae, in a type 1a supernovae, the canonical scenario is you have a white dwarf, so we are dealing with an object that has a maximum mass of 1.4 solar masses, and the whole star will be disrupted by the explosion. Okay, there are a few cases in which this is not the case, but in the standard mechanism of explosion, you get rid of the whole star. So the answer is clearly 1.4 solar masses. That's more precise.
Okay, thank you. The other one is about what about non-symmetrical effects? How important are, or how spherically symmetric are stars?
They are really important. Okay, actually, some mechanisms require non-spherical explosions to account for a number of observed phenomena, including the detection of gravitational waves, for instance. Okay, but again, from the point of view of modeling, and Raphael is one of the experts here. Remember that we are at the verge of starting to introduce rotation in models. Okay, so there is a lot of things to explore, and unfortunately, most of the detailed simulations, multidimensional simulations, still cannot proceed through the whole. You cannot run a full simulation from the beginning to the end, following everything. I mean, a star that undergoes first a common envelope phase in a binary system, rotates, how much angular momentum gets lost. I mean, we are far from there. So we know that these non-spherical effects are relevant, but I think we are still far from having a definite answer to that.
Okay, somebody earlier asked me about your book, so I don't know if before I ask the next question, if you can put back the information about your book and, for example, where can it be purchased?
Wow, hard to say. I suppose. I mean, it was available in Amazon. I didn't check because honestly, it's not my business. My business was to write it. But in case it's not, just let me. I mean, I encourage people to send me an email. If somebody wants to find it, and then I will push the publisher to make it available again. Okay, but I mean it's relatively recent, it's from 2016, so I'm sure they still have copies available at the publisher company.
Okay. Next group of question is a follow-up from a question about non-spherical effect, about the various uncertainties. So and also the effects of multiple systems. How do we know more about multiple systems? What are the uncertainties in the stellar modeling that you're most interested in?
Yeah, they are. I mean, the classical suspects to mention in these questions are precisely the common envelope phase. That's the. I would say it's the worst. That's the worst. That's the most poorly known phase in the evolution within a binary system. Associated to that, in second category, I would mention mass loss. Okay, again, this is something that we don't know for sure precisely, and there are different prescriptions that suggest larger values or lower values for that. I think that in terms of binary, these are the two ingredients that actually are well, among my favorites that we don't know we don't know in detail.
Okay, thank you. I'm scrolling through the other questions, seeing which one to ask next. There's one question. This could be also maybe answered by future talks, but I'm sure you can add some comments. Why disorder: hydrogen, helium, carbon, neon, oxygen, silicon?
Ah, that's a very good question. Yeah.
Why
again,
oxygen not before neon?
Okay. Well, I mean, why hydrogen first is something that is very easy. I mean, remember the process in which a star is formed, okay? So you are essentially driven things through gravity. You are increasing by, when you are contracting a chunk of material, temperature increases simply by compression, okay? At some point, when you think in terms of fusion, you have to overcome, repulsive barriers. So the easier species to approach in a fusion process would be a hydrogen nucleus or proton, okay, and another hydrogen nucleus, okay. So that's the simplest process that would require lower kinetic energy for the particles to undergo fusion and then overcome the Coulomb repulsion, okay. Then the idea is that why we start with hydrogen? Well, because that's the simplest nuclear structure that we have around. Okay, that's followed by helium. I would say in a natural way. Okay, and then again, there is a mixture of issues. Okay. In some cases, what we have are photodisintegration reactions that appear for a while and seem to change the dynamic of this series of progressions. You don't go element after element because, again, when you perform fusion of helium, what you obtain essentially is carbon-12. Okay, so you don't go to the next element in the periodic table, so you don't go through lithium, because again, the product of helium burning is not lithium, it's carbon. Okay, so again, the idea is that more or less you follow, roughly speaking, the order in the periodic table, but you have to take into account which are the products of a certain nuclear stage, and the fact that in between there are processes like neon burning, which is essentially not really a process of fusion as the others, but is driven by photodisintegration, so reactions carried by photons. Okay, that's the reason of this disagreement in the order, I would say.
Thank you, Jordi.